Hello, welcome back to Math 332 Linear Algebra. In this video, we are going to continue our discussions on the concept of orthogonality. In particular, we are going to look at the so-called fundamental theorem of linear algebra. So before we do that, let's do a very quick review. So suppose you have vector u and vector v. These are the vectors that is in Rn. We will be able to figure out whether or not these two vectors are orthogonal to each other or perpendicular to each other by looking at the dot product. So we know that the dot products of these two vectors, if it is 0, then they are orthogonal to each other. And also, if they are orthogonal to each other, the dot product will be 0. That means that the dot products will give us this information on whether or not the two vectors are orthogonal to each other. And also try to remember that this is vector in Rn, this is vector in Rn, but the dot products of two vectors is going to be just a number. So this is a number 0, not a vector 0. So this is a very useful tool to determine whether or not two vectors are perpendiculars, orthogonal to each other. What you need to do is just look at the dot product. And the next concept that we actually have studied in the previous video is a concept of orthogonal complements of a vector space. So suppose you are in Rn, and that is a vector space W. So this is a vector space. And we are going to look at something that is called the orthogonal complements of that vector space. So what is that? So in writings, the notation is this, W perp. So W perp, which is the orthogonal complements of W, is a set consists of vector U, which is in Rn, such that U dot W equal to 0 for all W that is in W, which means that you are looking elements that's in this set, elements such that, let's say this is U, such that the dot product with the elements here in W will be 0. Element here, okay, dot product of this U and this elements will be 0. U and this element will be 0. U and this element will be 0. In fact, you are looking for a vectors that is orthogonal. Okay, dot product equal to 0 means they're orthogonal. So you're looking for vectors that is orthogonal to every vectors that is in W. If you can find such a vectors that is orthogonal to every vectors that is in W, you put these elements into this set. So the collection of all such elements is what we call the orthogonal complement of that vector space. So we know that one of the it might looks like you might not be able to find such a vectors like that is orthogonal to everything in that vector space, but actually this 0 vectors is in W perp because 0 vectors dot any vectors is going to give you 0. They're orthogonal in a sense, okay, with every element that is in W. So 0 vectors is actually in W perp. So W perp is actually not an empty set. And this is technically very difficult to do because besides, except the very trivial kind of subspaces, like a subspace of vector space which consists only of 0 vectors, other type of vector spaces has infinitely many elements. So in order to do this, in order to find W perp by going through the dot product with every element in that space is not practical because that vector space has infinitely many elements. And we look at this example and this theorem before in a previous video, that in the situation, in the case where the W, the vector space, is spanned by, let's say, two vectors, W1 and W2. So in these situations, W perp is pretty easy to compute. So this is a review. If you forgot about this part, you will have to look at the previous video. But what it says is that if you can find a vector U such that the vector U, the dot product of vector U and W1 is 0, and U and W2 is 0, then this U, okay, with this two property, dot any vector that is from W will be actually equal to 0. So this is for all the W that is in W, this W. So when your vector space is spanned by some vectors, then in order to find W perp, you don't really have to go through all the element in W. You just have to make sure that the vectors that is in W perp is orthogonal to W1 and W2, which is sort of like a key player in that vector space, because everything in this vector space, we will be able to characterize them. We know how the elements in W looks like. In fact, all the elements in W is written as a linear combination of W1 and W2. That's the reason why that if the dot product with W1 and W2 is 0, then the dot product with the element that is in the span of W1, W2 will be 0. So in this case, W perp is actually going to be all the U in Rn, right, such that U dot W1 equals to 0 and U dot W2 equals to 0. Okay, now you might say that what happens if my vector space is not spanned by something? Well, a lot of the very important vector spaces are actually spanned by some vectors. So for example, column space is a vector space that is spanned by the column vectors, right? So this is the column vectors, right? Row space of A is also a type of vector space that is spanned by some vectors. In this case, there will be the row vectors, right? Row vectors, so on and so forth. So for this kind of vector spaces, the orthogonal complements is actually pretty easy to compute, and you will see that in a second. That's how we're going to find the orthogonal complement of these vectors. So this is something that you will need to remember, because fundamental theorem of linear algebra will utilize all these facts that we just discussed. So let me summarize it a little bit so that you will be it will be clear when we use it. So remember, if you have a vector space that is spanned by some vectors, let's say W1 and W2, right? So W perp will actually consist of all the vectors, right? Such that U dot W1 equal to 0 and U dot W2 equals to 0. And this goes both way. Okay, so if you have a vectors that dot product, the dot which is orthogonal, if you can find a vector U which is orthogonal to U1, you can find a vector U that's orthogonal to U2, you will know, and you can find a vector U that's orthogonal to W1 and vector U that's orthogonal to W2. Then if W1 and W2 span the space, then you know that this vector here U will be in the orthogonal complements of this vector space. Okay. So we should have enough review so that we can now look at the things that we want to look at today, which is the fundamental theorem of linear algebra. So this is a very important theorem. In fact, we will use it in developing a theory in the least square methods. So this is not a course where we just give you formulas and ask you to memorize some formula and apply it. We will have to show you why and how we get those formulas. And by doing that, one of the key things that you need to be able to follow is we are going to use something called the fundamental theorem of linear algebra, and that is critical for our development of a theoretical result for least square methods later. Okay, so now with that, let's look at what fundamental theorem of linear algebra say. So it says that, suppose you have a matrix A. So let's start with a matrix A. It doesn't have to be square. It's a rectangular matrix, m by n. Okay, so we know that if you have such a matrix, we can look at the column space of A, we can look at the row space of A, we can also look at the null space of A. And you can also transpose this matrix. So if you transpose this will be n by m now. Again, you can also look at the column space of A transpose, row space of A transpose, and null space of A transpose. These are all vector spaces. Okay, and so here, the fundamental theorem of linear algebra is try to make some connection between all the spaces. So the first thing what it says is that if A is a m by n matrix, okay, if A is an m by n matrix, then the orthogonal complements of the row space of A is the null space of A. So the orthogonal complement of the row space of A. So this is the row space of A, and this is the orthogonal complement of the row space of A. So let me say that again. This is the row space of A, and this is the orthogonal complement of the row space of A. And it says that the orthogonal complement of the row space of A is actually the null space of A. Okay, so this is the first thing they want to talk about. Okay, and the second thing it's saying in that theorem is that the orthogonal complement of the column space of A, so this is the column space of A, So this is the orthogonal complement of the column space of A. Let me say that again. This is column space of A. This is the orthogonal complement of the column space of A. And according to the theorem, this is actually the null space of A transpose. That is what they're trying to say. So this is the second equation right here. So this is what fundamental theorem of linear algebra is about. Okay, another thing, if you remember from the previous video, something that we state without proving it, is that if you have a vector space W, and we show that W perp, the orthogonal complement of this vector space, is itself also a vector space, so we can look at the orthogonal complements of W perp. So that will be orthogonal complement of W perp. So this is W perp perps. W perp perp is the orthogonal complement of W perp, and this turns out to be W. So because of this theorem, okay, because of this theorem, we also have the following. This is going to be equivalence to these two equation right here. So for example, let's look at the orthogonal complements of the row space of A. It is equal to the null space of A. So now if you apply orthogonal complements to this, you apply orthogonal complement to this, then orthogonal complements of the row space of A of, the orthogonal complement of the orthogonal complements of the row space of A is just the row space of A. So we have that. That is the same as equation star. They are logically the same. They are equivalent, okay? And we will also have from equation double star that if you apply the orthogonal complements to this orthogonal complement, then you get null space of A transpose complement. Then this orthogonal complement and complement again will give you the column space of A is equals to the orthogonal complements of the null space of A transpose. So basically this is the second equation. So they're equivalent to the second equation, and this is equivalent to the first equation. All right, so we are going to look at the proof, okay, of one of the statements. So right here, we are going to look at the proof for equation star. That is, we want to show that the null space of A is the same as the orthogonal complement of the row space of A. And the second equation here will be a homework problem. So this is going to be a homework problem. It is not very difficult. If you understand what's going on for the proof for the first equation here, then you will be able to reproduce this, and you'll be able to do that in your homework. So we are going to only look at this statement right here, okay? And that is what we're going to do for the rest of this video. And let's get to it. So, but before we do that, let's just try to remind you that if you have two sets, let's say this is set P, this is set Q. So this is set, this is also a set. Now, how do you show that the sets P and the sets Q are the same set? Well, we mentioned this before. In order to show that two sets are the same, you first have to take an element from P and show that this element from P is also an element of Q. So you want to take an element from P and show that if you have an element from P like this, okay, you will have to find, and this element is also in Q. And if you're able to show that this is true for all the element in P, which means all the element in P is in Q, then you will show that P is actually a subset of Q. And then you have to reverse and show that if you have an element here in Q, then that element will also be in P. So if you can show that all the element in Q is also in P, that means that Q is a subset of P. So once you establish these two inclusions, you will be able to conclude that actually these two sets are the same. This is how we show that two sets are equal. This is set equality. Set equality means that every element in here is in here, and every element in here is in here. Okay, so now space of A, okay, is a set, right? It's a vector space, but vector space is a set. Row space of A complement is also a set. So this is a set. So in order to show that equal, we'll have to first show this inclusion and then show this inclusion. So in order to show this inclusion, we will have to take an element. So we'll have to take an element X that is from the null space of A, right? And we want to show that this element is also being in null space of A will also be in the row space of A perp. Okay, so if you can establish that, then you will establish that this inclusion. even though we are like checking just one elements, but this is not, this is what we call fixed but arbitrary elements. So if this work, then it will work for all the element that's in null space of A. So therefore you have these inclusions. Okay. All right. So we are going to do just that. Right. So let's look at this. Okay. Now we're going to follow this and we're going to do just that. Okay. So let's, okay. All right. Okay. Now, so let's take an element x that is in the null space of A. What does it mean? If your x is in the null space of A, then we know that A of x will be equal to 0. That's the definition of a vector being in the null space of A. So we are going to write, okay, oops, let's clean up this one. Let's clean up this one. Okay, let's clean up this one. Okay, all right. Okay, so x is in the null space of A, means that A of x will be equal to 0. So we are writing out the A. Okay, so we write out matrix A, and we indicate the row of the matrix. So this is the first row of this matrix A. This is the m row of this matrix A. Your A is m by n, right? So you have m row, Minnesota, m rows, okay, and n columns. So we have m row. So when we multiply this matrix, notice that when we multiply this matrix, we will take this and multiply this to get this 0, right? And then we will take the second row of this matrix and multiply this column and get the second 0. And then we'll take the third row of this matrix and multiply this column and get the third 0, so on and so forth. And at the end, you get this m row, multiply this column to get the last 0. That's how we multiply this matrix, these two matrices, right? Row and then column, row and then column. Now, so let me show you something here. So this is an example before we move further. So if you have a matrix, first row is 1, 2, and 5, let's say. Okay, and then here you have x1, x2, and x3, and then you have a 0 here. So you have some of the stuff here, some of the stuff here, some of the stuff here, some of the stuff here that we don't really care right now. Now, by doing this and this, okay, so when we multiply, we'll be doing 1 times x1 plus 2 times x2 plus 5 times x3, and this will equal to 0. That's how we multiply a matrix, row and then column. Now, another way to see these operations is to take this row and transpose it. So it's supposed to be a row vectors, but now we transpose it and make it become a column vectors. So now the one that we saw before is the same as if you are taking the dot product of these two column vectors. So the operation that we just did just now to get 0 is the same as doing this. Okay, so let's see it one more time. So if we multiply matrix in the traditional way, we will have n1x1 plus 2x2 plus 5x3 equals to 0. Now, if you take the row vectors, transpose it so that you become a column vectors, and you take the dot product, you will get 1 times x1, that's how you do dot product, plus 2 times x2 plus 5 times x3 equals to 0. So you see this right here, 1, 2, 5, 0, 1, 2, 5, 0 is exactly that. So one way, so this is hopefully you get this one. So one way to look at the matrix operations, this times this equal to 0 and so on and so forth, is to transpose. The row vectors and become a column vector. So this multiply this equal to 0 can be written as the row vector transpose dot the x vectors. So the x vectors here is x1 all the way to xn. Okay, so as I said before, this operation here, traditional matrix multiplications, is the same as you are taking first row transpose, okay, dot the vector x and set it equal to 0. The second one here will be equivalent to taking the second row of the matrix A, transpose it so that we become a column vectors, dot the x vectors and set equal to 0. So you get that. So all this operation that you multiply will be equivalent to all this. So you have Rm transpose dot, okay, so these are row vectors, transpose it, become column vectors. Your x is always a column vectors, and you get 0. So you can see from here, X being in the null space of A, X being in the null space of A, give you that this X, okay, X being in the null space of A give you that this X is actually orthogonal, okay, it's actually orthogonal to what? It's orthogonal to R1 transpose, orthogonal to Rm transpose, orthogonal to all these vectors. Okay, so this is what we try to say here. So X being in the null space of A give you the fact that X is actually orthogonal to all these vectors. Okay, but okay, so from the previous video and actually from the discussion that we have just now, so if your X is orthogonal to all these vectors, so if your X is orthogonal to all these vectors, your X, okay, will be in. Okay, let me say one thing before jumping the gun. So X, okay, X is in the null space of A, meaning that X is orthogonal to all this. So if you form a vector space, which is a span of R1 transpose, R2 transpose, all the way to Rm transpose, if your X is orthogonal to all this, and if you look at this vector space, then, okay, your X will be orthogonal, will be in, okay, the orthogonal complement of this vector space. Okay, so let's look at it slightly carefully. So what is this vector space, by the way? What is this vector space? This vector space, so these are row vectors and then you transpose them. These are the row vectors and transpose them. So think about it like this. Think about it like this. So if, let's say, this is an example, okay? This is not a proof or anything. This is an example to help you understand. So you have like 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's say this is a matrix A. So you take the row and then you transpose. So you have 1, 2, 3, okay, 4, 5, 6, okay, and then 7, 8, 9, right? If you look at the span, of all these vectors, this is still the row space of A. This is still the row space of A because the linear combination of these vectors is the linear combination of these vectors. These are the row vectors. You just flip it and make it become column. But if you look at the linear combinations of this vectors, these are actually still the same as the linear combination of all these vectors, the row vectors right here. So I'm saying, so this requires a little bit of thought, but I'm saying that all this thing here, if you look at all the linear combination of this row vectors transpose, it is actually still going to give you the row space of A. They are the same. So this span of all these row vectors transpose is actually still going to give you the row space of A. If you still don't quite believe it, just play with the example and you will see it. Okay, you play with some example and you will see it. So X is orthogonal to all this component, right? So from the previous review, we know that that means that X is going to be an element in the orthogonal complements of this space. Orthogonal complement of this space, but this space is the row space of A. So X is actually in the orthogonal complement of the row space of A. So X being in the null space of A will give you X is actually in the orthogonal complement of the row space of A, which means that the null space of A is actually a subset of the row space of A perp. Okay, so that's what we have been showing. So let's go back to the notes and you can see this is what we've been showing. So let's look at this thing right here, get rid of that. So you see that X is in the null space of A, means that AX equal to 0, means that we have all this, means that this X, okay, is orthogonal to R1 transpose, is orthogonal to R2 transpose, all the way to Rm transpose. So because of that, R, if you look at the span of all this R1 transpose all the way to Rm transpose, which is the row space of A, then by having this means that your X is actually in the orthogonal complement of this space. So your X is actually in the orthogonal complement of this space, and that is what we have shown. Being an element in the null space of A implies that you are in the row space of A perp. Now, so in order to show that these two spaces has to be the same, we have already showed this. We have already showed this. So now we'll have to show the other inclusions. Okay, so now we'll have to show the other inclusions, and that will be here. So which means that now we're going to take an element from the row space of A perp, and we want to show that it is in the null space of A. So this is going to be given by this proof right here. But this is actually a inclusion that's slightly easier to show. Okay. Okay. So if you don't believe me, let's look at it. Okay. So what do we have? So now suppose we take an element that is in the row space of a perp. Okay, and we want to show that that element will eventually be in the null space of A. So if you manage to do that, then you are showing these inclusions. So from the previous inclusions together, take two of them together, you will actually show that we have this set equality. We'll have this set equality, and we are done. Right. So how do we do that? So now suppose that X is in the row space of A complement. Okay, orthogonal complement. So you are in. So now your X is in the row space of a perp. So what does it mean? It means, right, X, okay, dot everything that is in the row space of A will give you 0, right? Being in a vector space perp, right, being in W perp means that U, if it is in W perp, means that U dot everything that is in W has to be 0, okay? So now let's look at this space, okay? So this is like our W, okay? So now this X is in the row space of a perp. That means that X is orthogonal to everything that is from this vector space. But row space of A has a lot of stuff, but it definitely have the first row of the matrix, the second row of the matrix, and so on and so forth. So in particular, X dot R, which is the row of the matrix A. So let's say R1 is the first row of the matrix A. We can't really take X dot this one because X here is a column vector. Here is a row vectors. So if you want to talk about dot products, you have to take R1 transpose. Okay, so what it means is that, if you take the row, if you take the first row, okay, of this matrix A, if you multiply with x1 all the way to xn, so this here will give you 0. This here will give you 0. How do we know that? Because X is in the row space of a perp, means X is orthogonal to everything that is in the row space of A. In particular, X is orthogonal with the first row of A. So X is orthogonal with the first row of A will give you this. X is also orthogonal with the second row of A. So X orthogonal to the second row of A means that when you do this with this, you will get the second 0. So go through it one by one, all the way to the M row. X is in this space, means that X is orthogonal with the M row of A. That means that this with this will give you 0. So you will see that X is in the row space of A perp, will means that X is actually in the null space of A. Why? Because this is A, right? This is matrix A, this is our X, right? And this is our 0. So X is being in the row space of A perp means that A of X is actually equal to 0. So A of X is actually equal to 0 means that your X is actually in the null space of A. So that gives you the proof that X is in the row space of A perp, then X is actually in the null space of A. So we have the second inclusions. So together with the first inclusion and the second inclusions, we will make this equality. So we'll make this equality. So the null space of A and the row space of A perp is actually the same thing. Okay, so that's the end of the proof. And before we finish this video, let me just do a diagram of what's going on. So what he's saying is that the row space of A, you have seen this kind of diagram in some of the books. Row space of A and the null space of A is kind of like orthogonal complement with each other. This is kind of like a diagram. It's a fake diagram. It's just a diagram, not the real thing. Okay, so it's kind of like indicate this is like 90 degrees right here. So row space of A and the null space of A, they are orthogonal complement to each other. And we also have another one right here, which says that if you look at the column space of A and the null space of A transpose, okay, has this relationship. They are orthogonal complement of each other. This is a diagram made famous by MIT professors. His name is called Gilbert Strang. He wrote a lot of book. He have a lot of linear algebra video, which is how I learned linear algebra in year 2001 when I was an undergraduate. During that time, you still have to dial in. It's a big modem, and then you have to dial in, and you have to download the video. You like it takes like 2 hours for you to finish one like YouTube style of videos. Well, but anyways, you can still find all those videos online. It's under MIT OpenCourseWare, and his book is really fun to read. His book is a kind of a book that is having a conversation with you. It's like telling a story and explaining. It's not a lot of books in mathematics is very dry in the sense that they give you a theorem, proof. This one will kind of like try to motivate the idea by having a conversation with you. So it's fun to read if you don't really know the subjects. But if you already know the subjects and you want to find a quick reference, that book will be very annoying because the theorem are not stated very clearly. I mean, it's hidden in the story, but it's not difficult to find. And if you are in a rush and try to find them, it's going to be pretty painful. So this is what we call the fundamental theorem of linear algebra. And you have to kind of like mimic the proof that you have seen just now and try to establish the other proof, that is the column space of A and the null space of A transpose. They are orthogonal complement of each other. So another way to state this theorem is that the row space of A and the null space of A, they are orthogonal complement of each other. If you take this perp, it will be equal to this. If you take this perp, it will equal to that. Okay, right? And the column space of A and the null space of A transpose is also orthogonal complement of each other. If you take CA perp, it will equals to NA transpose. If you take NA transpose perp, it will equal to CA. Okay, all right. So that's it. I'll see you in the next video.